Hello, my name is David Wilson. This presentation will discuss the Hall effect. Let me start with an overview. First, I'll give a brief history of the discovery of the Hall effect. Next, I'll cover the theory behind the Hall effect. I'll also describe typical construction of commercial Hall effect sensors, and I'll conclude with a video demonstrating how Hall effect sensors can be used in place of brushes for commutating DC motors. The phenomenon now known as the Hall effect was first discovered by Edwin Hall in 1879 while working on his PhD at Johns Hopkins University. He was experimenting with current-carrying materials in magnetic fields and detected a voltage across the material perpendicular to the applied current. Of note is that Hall's discovery came 18 years before the discovery of the electron. The importance of this will become apparent as we discuss the theory behind the Hall effect. To describe the theory behind the Hall effect, we first begin with a slab of conductive material. Next, apply a current along one axis of the material. Finally, place the slab in a magnetic field that is roughly perpendicular to the direction of the applied current. The applied current will cause free electrons to move. The speed of this movement, referred to as the drift velocity, is a function of the applied current, the volumetric density of the free electrons, which is the number of free electrons per unit volume of the material, and the area of the material normal to the applied current, and finally the charge of the electron. The Lorentz force law states that a charged particle moving through a magnetic field will experience a force. The force is given by the vector cross product of the drift velocity and the magnetic field vectors and scales with the charge of the particle in question. Now back to our slab model. The magnetic force causes the electrons to move toward one side of the material. This results in a non-uniform distribution of electrons, here from top to bottom. This also creates an electric field. Electric fields also produce forces on charged particles. The electrons will continue to move towards one side of the slab until the force due to the resulting electric field is sufficient to balance with the magnetic force. Equating these two forces allows us to solve for the Hall voltage. Therefore, the Hall voltage can be completely explained by the Lorentz force law. Today, many various types of Hall effect sensors are readily available. However, they all have a few basic features in common. For one, they must be able to cope with the fact that the Hall voltage is typically very small, on the order of microvolts. Therefore, commercial Hall effect sensors typically include an amplifier circuits to boost the Hall voltage to more useful levels, on the order of a millivolt to a volt range. I'll first demonstrate a commutated DC motor. Here we have a DC motor with permanent magnets on the rotor, electromagnet on the coil for the coil, power supply to power it, prototyping board for making connections. The circuit is set up to flow from positive through the coil, and for the coil to get to ground it has to go through these commutator brushes. These commutator brushes would be closed in when they contact these aluminum strips on the rotor, and then there's gaps in between where there is no metal, and in those places the circuit would be off and allow the motor to rotate. So these allow the circuit to complete. And you see when I touch it, the motor will start up. The downside to brushes, there's significant arcing, rubbing, and friction on these parts. So that's a downside to traditional brushed DC motors. I've now replaced the brush type commutator with a Hall effect sensor. It's on the back side of this post. The Hall effect sensor in this case responds to the south pole of a magnet, closing the circuit just like the aluminum strips did before with the commutator. That weak Hall effect signal is sent to this power transistor, which acts as a solid state switch to turn the motor on. Now I've made no changes to the power supply for voltage, but notice how much faster and quieter the motor runs. There's no cracking, there's no arcing, much less friction. This motor would last a lot longer than a brush type motor. The length of time it takes it to slow down is also an indication of very low friction.